Okay, so thank you for invitation to this wonderful city, this fantastic Venice. And my name is Helena Reichlova. I'm from Institute of Physics at the Czech Academy of Sciences and Solid State Physics of the Technical University of Dresden. And I will speak about spontaneous anomalous Hall in the altermagnet. And this work was done in a broad collaboration of many people, and very importantly, the experimental work which I present is motivated by theory prediction of Tomáš Jungwirth, who will have also his talk during this conference, and Libor Šmejkal and Chairosinova from the Mainz University. So spintronics, we already heard something about it. And we also heard something about antiferromagnets, or which are one type of compensated magnetic systems. However, surprisingly, I didn't see this slide yet, so I will very quickly go through the advantages, why we bother with antiferromagnets, why we bother with the compensated magnets. So the first motivation for me is the natural scientific curiosity. So which effects, which we know from the ferromagnetic spintronics, can also work without the net magnetization. This is the fundamental question. However, there is also the strong application or technological motivation to sort of go beyond the standard ferromagnets. And this is given by some intrinsic limitations of the ferromagnetic systems, which are the well-known density of integration, speed, the robustness, where the ferromagnets are reaching limits. We know the stray field, the speed limited to the gigahertz range. And this is where the compensated systems, or the antiferromagnets in particular, can be of use, because they are not sensitive to the stray fields. They do not generate the stray fields, and they are not sensitive to external fields. And their reversal dynamics is in the range of terahertz. But then there is the last point, which I find especially important, and this is that the compensated magnetically ordered systems are actually much more common in nature. They are much more often found. And very importantly, they are found with various carrier concentrations. So they are metallic, as we heard already in the very nice talk in the morning. But they are also semiconducting. There is many intrinsic antiferromagnetic semiconductors. There is many insulators. So we have the full range of electronic properties. And this I find especially important in research fields like thermoelectrics or spin-caltronics, which I really like. And here we have to have multiple parameters optimized sort of simultaneously to achieve maximal figure of merit. And for that, naturally, we have to have the choice of having multiple or tunable carrier concentration, which the antiferromagnetic or compensated magnetic systems can deliver, can provide us. On the other hand, there are also disadvantages, and these are related to the lack of the stray field, which is especially that they are hard to detect and manipulate. And also, as we heard, the workhorse or the phenomena in which why the ferromagnets are popular in applications are the gigantic magnetoresistance and the spin transfer torque switching, which was very nicely discussed yesterday. And can we have these phenomena also in the compensated systems? So the detection and manipulation in the last decade, there was a significant progress when the anisotropic magnetoresistance or the tunneling anisotropic magnetoresistance was employed to show the spintronic functionality, to show the first proof of principle experiments in these papers, for example, and I will not speak about it more. And there was ongoing discussion, can we have also the effects which rely on breaking of the time reversal symmetry in the band structure. And also in that research direction was a huge advancement done in the last several years with the milestone experiments when Nakatsui and Nayak showed that the anomalous Hall effect can indeed be present in compensated systems. And anomalous Hall effect is one of the important spintronic phenomena, and it has two, let's say, related phenomena in the spin caloritronics or magneto-optics. And also these two phenomena were demonstrated experimentally in these papers. And I show these three panels next to each other, and what makes them sort of what they share is that the material of choice in that case was a non-collinear system, in particular mangan 3 tin. So these were measured on these non-collinear systems, which were one way how to get around the limits which were before seen in the collinear systems. And these two techniques, this anomalous Nernst effect and magneto-optical Kerr effect, are for us experimentalists especially important because they can enable for us to visualize our magnetic structure. This is something which we really like because with antiferromagnets and generally compensated magnets, this is really not trivial. And we have shown that the anomalous Nernst effect can be generated locally by a laser gradient. Laser can generate a local thermal gradient, which when be then scanned over the sample surface, the globally detected thermal voltage is recorded, and depending on the local position of the laser, the local magnetic contrast is detected, and therefore it yields spatial information about the magnetic properties. This is sort of enabling technology which was used on several non-collinear magnetic systems already. And similarly important is the work of Higo and others, where they show that by the magneto-optical Kerr effect, one can visualize the magnetic domains in non-collinear system, which is again very important once we want to go further in any domain motion or even any racetrack or anything. So, but these are the non-collinear systems, which are one very fascinating area of research. And in these systems also the GMR was predicted in the paper by Jakub Železný, which was already mentioned also here. However, the experimental demonstration is so far not completely here, and it can be related to the loss of the spin coherence in this non-collinear system, which is simply the characteristic of these systems. And the question is, what about the collinear? Should we then are they really doomed to show the anomalous Hall effect, to have any hope for the GMR or spin transfer torque? And the answer is no. And this is what I will speak about. And this all is based on the recent or 3 years back theory prediction of Libor Šmejkal and Jairo and Tomáš, which looked once more at the magnetically ordered material based on the symmetry argument. Simply look at the magnetically ordered collinear materials without any spin orbit coupling, and let's try to understand them. So we know the ferromagnetic systems, they have the spin arranged in one direction. They are these materials which industry likes, which we like them for gigantic magnetoresistance. They have the net magnetization, and they have the breaking of the time reversal symmetry and the spin polarization in the band structure. Then we have the antiferromagnets, which are also one of the topics of this conference. They have many fascinating properties, many advantages, which are very often related to the absence of the net magnetization, which has a lot of benefits for also the application. However, they are not having the time reversal symmetry in the band structure. These are the generate spin up and spin down, and there is no spin polarization. But the potential is still there, especially on the speed end and on the versatility and the choice of material end. And then there is a third class of magnetic materials which combines some of the advantages of the ferromagnets and of the antiferromagnets. However, it still has additional benefits. It still has additional unique features which are not present in none of these previously discussed classes. And let me show you just a very brief, very simplified picture of what do we mean by this new class of magnets. So typically when we think about antiferromagnet, here we see the compensated system without zero net magnetization. And then when the time reversal symmetry is applied and we shift it by a half unit cell, we recover the same picture. Therefore, the time reversal symmetry in the band structure is present. However, when we now do not see our spins as sort of lonely balls somewhere, but we look also at the non-magnetic environment, we can come up to such a scenario that these non-magnetic cages of the non-magnetic atoms, which are formed around our spin-carrying atoms, they break the time reversal symmetry in that case, because when I now flip all the spins, I cannot simply shift it by a half unit cell because here the non-magnetic environment is different. And similar scenario, which will be actually in more details discussed now in this experimental part, is that also by having, for example, these collinearly arranged spins in a hexagonal cage also does not allow us to flip and shift because the time reversal symmetry would be broken. This real space magnetic properties translate into the momentum space as opposite spin polarization on the magnetic sublattices, which are then connected by such a rotation. And energy cuts, shown like schematically here, already show one of the unique features of this class of materials, and that they are having no net magnetization, as we know from antiferromagnets. However, they still have the spin polarization, and moreover, this polarization is anisotropic. Therefore, it depends on the crystal direction. This unique combination of properties and this large promise for our spin transport community and this alternating spin polarization led to the name altermagnets. So coming back to our table, we have here our altermagnet class, where the zero net magnetic moment is something which they share with the antiferromagnets. And still there is a spin polarization present, which they partly share with ferromagnets, but these anisotropic properties makes them really unique. And this makes them also very promising for high-speed GMR and so on. And so now the experiment, what I will speak about is one of the altermagnetic candidates, which is mangan-5 silicon-3 thin films. So before I go to the thin films, let me briefly introduce the mangan-5 silicon-3 bulk material. It's relatively well-known material which was studied, for example, by these gentlemen. And it shows two magnetic transitions which are at approximately 160 Kelvin. And this magnetic transition is from the paramagnetic phase to the collinear and this non-collinear phase. And they are associated also with structural transitions, so the hexagonal to the orthorhombic and monoclinic crystal structure. These bulk materials, they were well studied by various techniques, confirmed all the transitions, and also the polycrystalline films were fabricated by Christoph Sirges, and he showed that this non-collinear phase in the low temperature leads to a topological Hall effect. And now we prepared thin films which were epitaxial and which were grown on the silicon 111 substrate. The important thing is that when it's grown on this silicon 111, it stabilizes the hexagonal unit cell in the full temperature range. This is very important thing, and I will come back to it later. And it's so important that we put additional effort to really confirm this assumption or this suspicion which we had. So we took the samples to the low temperature X-ray synchrotron, and indeed these are the bulk data reported by Mr. Brown and others, which show these two structural transitions which accompany the magnetic transition. And what the thin film do, they indeed reproduce the C direction. This is the one which is free to move because it's not constrained to the substrate. However, the one which is constrained to our silicon substrate, it does not have the freedom to move, and it stays constant. So the hexagonal unit cell, this is what we have. So from these films, we fabricated our hole bars. And it's a standard hole bar. We apply the current along the main channel and measure the transversal and longitudinal voltage. And we first look at the resistivity as a function of temperature. And from these two kinks, we already see that something is a bit different than for the bulk, that the second transition, the second magnetic transition shifted up to the higher temperature to this 240 K. The first one stayed approximately at the same temperature. And we also started by doing a lot of magnetometry measurements, and we measured at the 50K, 100K, 200K, 300K, and in all these data we could detect some very weak moment below our resolution of this 0.01 more magneton per manganese. And this is in striking contrast to the magnetotransport data which we did, where we see a robust, clear, anomalous Hall effect, basically in the full temperature range where the mangan, when our films are magnetically ordered. This is then the clear indication that we indeed have a time reversal symmetry in the band structure in our collinear material. And now I want to look a little bit more in detail in our measure the data. So already here one can see that there is a feature which can be associated with the low temperature phase. And how do we actually get this feature out? So we simply take our raw data. This is exactly as we measure it. We subtract the ordinary Hall effect, and then we extract the anomalous Hall effect, and the remaining part I call here rho XYT. And this is indeed present only in the low temperature phase, and it's also consistent even in the amplitude with Christoph Sirges and his polycrystalline films. So here, all good, it seems that we are fine, but what is the very interesting and important thing is that all the signal is actually dominated by this robust, clear, anomalous, spontaneous part, which I plot here, which seems to be independent on the first magnetic phase transition and is completely absent in the paramagnetic phase. Here I just plot the calculated anomalous Hall conductivity, which is approximately 5 to 10 Siemens centimeter, and also the coercive field, which is usually some sort of indication also of some transition, but in our case it remains constant in the full temperature range when the sample is magnetically ordered. We also detect simultaneously the magnetoresistance, which similar like the non-collinear, like this rho XXT, is present only in this non-collinear phase and is basically absent in the collinear phase where we look at. So now, when we have all this experimental evidence, we confirm the hexagonal crystal cell, we have vanishing magnetization, we have the spontaneous time reversal symmetry breaking in the band structure, and we have likely collinear structure. Then let's look what is the actual difference between the bulk and thin films. And here it comes back to the introduction, which I already mentioned that. Here, the bulk is reported to have the orthonomic structure. This is this gray thing. So these four manganese, which are the only one which are magnetically ordered, are actually doubling the magnetic unit cell. So here the time reversal symmetry is preserved, and this is completely inconsistent with the neutron data reported here. This is opposite to the thin films where the hexagonal unit cell is stabilized. There is no reason that there would be any doubling of the magnetic unit cell. And here when I flip the spins, I cannot do this shift as here, so therefore the time reversal symmetry is broken. And now, given that I have here my 4 ordered manganese in this hexagonal unit cell, I can kind of think what are the options. I still know that it's compensated. I know that my squid gives me no net moment. So what are the options how I can sort of arrange there the spins? They are basically these 3 options. And by the DFT calculation, this state is calculated like the ground state. And interestingly, it also calculated anomalous Hall effect gives us this approximately the same value of the anomalous Hall conductivity as we measure in our experiment. So I told you that the crystal purity is very important because this effect relies on our environment, on our non-magnetic environment. And so this we also confirmed experimentally that as during any growth optimization, we have samples of various quality. And you see that here, when we measure different samples, they, on the first look, these are the raw data as we really measure them in our cryostats. And you see on the first look, sometimes you have a robust anomalous Hall effect. Sometimes it's kind of a little bit not clear, and sometimes it's completely absent. And this can be very accurately correlated with the quality, with the phase purity of our samples. So when we have the mangan 5 silicon 3 as ordered as we can make it, then it gives the best signal. And we studied it systematically on one sample series where with changing the ratio of the mangan 5 silicon 3 and a spurious phase. And although they share some same feature, like the absence of the signal above the nail temperature, the amplitude, the magnitude of the anomalous Hall conductivity is scattered. And when we plot here the X-ray analysis, we extracted the ratio of the mangan 5 and the mangan silicon spurious phase. And here I add artificially also one polycrystalline reference sample which we prepared. And you see that the anomalous Hall resistivity can be kind of correlated, that it's increasing with the increasing ratio of mangan 5. This is in contrast with the squid measurement, where if we extract some moment which we measure, this moment cannot be correlated with our ratio of the mangan 5, and also cannot be correlated with our anomalous Hall conductivity. So I mentioned that this anomalous Hall effect has also related effects such as the anomalous Nernst effect. And this is something which, of course, interests us a lot. So we already prepared samples where we applied thermal gradient instead of electrical current, and we measured the transversal voltage. And indeed, we see a signal. We see saturation at similar. The colored data are the anomalous Nernst data, and they are overlaid with the anomalous Hall data measured simultaneously. And we see that the anomalous Nernst data, they share some common features. They share the same saturation field. They are also more or less constant in the full studied temperature range. However, there is also striking difference, and this is the absence of the coercive field in all anomalous Nernst data. And we already excluded some obvious experimental artifacts, which I don't have time to speak about, but this is definitely a thing which we wonder right now, why one has the broad coercive field and one does not. Again, topic for discussion, or happy for any ideas. And the Kerr effect, the second brother of the anomalous Hall effect, there is already recent predictions for the ruthenium dioxide, which is one of these textbook examples of altermagnets. So I think that the prospects for the community of optics and magneto-optics in this altermagnetic family are really, really large. Yes. So, so then last thing which I want to comment is that we showed, or I showed this anomalous Hall effect in our mangan 5 silicon 3, but even more important are probably the spin currents which we need and which are in the end the basis for some spin transfer torque and GMR. And these are indeed predicted in altermagnets. And moreover, they are anisotropic, so they depend on which direction we apply the electric field. We can generate transversal spin current or longitudinal spin current. Here one can just see that these ellipses are off-centered differently, so the excess of the spin generates a total spin current. And these were already also first experimental evidence present by these three groups, and I believe that there will be definitely more results soon. So this is kind of outlook. I presented the mangan 5 as an example of light element material which can have these altermagnetic properties. But there is also the metallic ruthenium dioxide, many nice experiments. There is the semiconducting altermagnet mangan telluride, where we also show the spontaneous anomalous Hall effect, and many other materials. And this brings me to the conclusion that we showed the anomalous Hall effect in an altermagnetic candidate mangan 5 silicon 3. And we have some indication of the anomalous Nernst, and I believe there is a prospect for magneto-optics and many more areas. So thank you for your attention.
Thank you, Helena.